Hi there. So let's use the same data set and the analysis tool pack under the data tab to get the output, a complete output of the linear regression. Over here, we're going to head to the data analysis and go all the way down to regression and hit OK. We're going to have to specify our y, our dependent variable. Height definitely depends on age, and then the input here is age, which is the independent variable. Do we have labels? Yes, I like putting labels there. And of course, the confidence level always is 95%, and we don't have to enforce the constant to be 0. We don't have to enforce that for now. So the output range, I would like the output range to be around this area. So this is sufficient for me. And I would like the output or the residual, I would like to see the residuals. And I would like to be, no need for standard residuals. I just would like to see the residuals for now. And normal probability plots is not important for me, because I'm looking at the normality of the residuals rather. All right, let's take a look. This is the output. It ranges from very top where we specified the output all the way showing us the number of observations. Here we have 12, and over here we have the predicted height. This is having a lot of decimals. Let's just put it in a way that we can easily see it. So I'm gonna reduce the decimals to 2, and here it is. And these are the residuals. Do you remember how we computed the residuals being the actual minus the predicted? Over here, it has been computed automatically for us. But I like to take you through computing it manually so that you can better understand what are these really. So we were able to compute these ourselves in the previous video, but over here they are computed automatically for us. So in the quiz, you don't have to compute any residuals unless I ask you to do so. You can find the residuals already done for you with this output. All right. Now you have the number of observations over here. You have over here the multiple R, which is the coefficient of determination, which is squaring the Pearson correlation. So as you can see here, the R is squared, or multiple R is 0.998. It's different than the R square. So we want the R square. So this is the coefficient of determination, the R square. So the R square here is 0.989. This is the multiple R. If you remember 0.994, it is this number. It is the Pearson correlation. So basically, if you square this by multiplying itself here, you will get the R squared. So I would like you to really know what are these. So multiple R is nothing but the Pearson correlation. R squared is the coefficient of determination. And over here, this is the adjusted R squared. For this example, we have only a simple linear regression, so we don't need to look into the adjusted. We just take a look at the R squared without the adjusted R squared. All right. Okay. Having this said, let's take a look at the standard error. You guys remember that we found the standard error 0.259 from the previous video by finding here the standard error with the function steyx. So it is all found for you simply with this, as you can see here, with this function. All right. What else do I need to show you? I'm going to show you here the interpretation. So we are going to say here with R squared that the interpretation is age explains a total of in percentage, that will be here equal this, and we put it in percentage, a total of 98.9% of the total variation in height in toddlers height. So age explains a total of 98.9% of the total variation in toddlers height. I am with the researchers who reject to say that this is necessarily a model fit kind of measure, but in some other books or some other researchers, they will tell you this is a strong indication and this model is really strong. But as you can see here with this example, this model is not necessarily strong if the intercept is there and we don't force it to be 0. So in any case, let's proceed with the second piece, important piece. So the first important piece actually is this. The second important piece is this. And basically, I need to make sure that I am using the 2 standard errors. The system here will find for me the 1 standard error, but finding the 2 standard error isn't difficult because we just multiply it by 2. So this would be the 2 standard error. And I want to make sure that these residuals lie within 2 standard errors. Or you can take the standard residuals and make sure none of them is greater than 3. So we can have here the if function. If the absolute value here of this residual is less than or equal to this value over here, and you need to basically either name it or give it a fixed reference. Give me 1, else give me 0. And then you get 1. This lies in within, and you can just copy to the end. And then you can just make the interpretation here, which is the sum of all these values as we've done earlier, right? Over the count or over the number over here of observations being 12. And that means, and we need it in percentages so that we can see how much is the percentage of residuals lying in within 2 standard errors. And we have 100% of residuals lie within 2 standard errors. So this is, I would like to highlight it also because this is the second very important explanation that I'm going to ask you for. And in the quiz, I don't want to have to wear thicker glasses than the one that I already wear. So I want you to use exactly the same locations, exactly the same style that I'm using right now to answer my questions. So it's easier for me to see the work. So that, are we done here? I'm going to show you here. What I'm going to do is just to put it in a nice, oh, okay. Okay, so I'm done here, and this is number 1. I'm going to put it here, number 1, the interpretation. Uh-oh. What's wrong? All right. So I would like to add here. Oh, okay, won't work. Okay. Anyway, I don't know why now it's not working with me. So this is number 1. I'm going to give it in here. And this will be number 2, basically. So please don't do what I just did right now. I forgot how I will add the brackets safely. So this number 2. And now number 3 would be over here. So number 3 is the interpretation. I'm sorry for the interruption here. So number 3 here is the interpretation of this hypothesis. This is a null hypothesis that says if age is actually a very important or not very important component in the model. So over here, we are looking for a value that is less than 0.05 to reject the null hypothesis that is null, negative, nothing in there. So null hypothesis in statistics say nothing in there, negative, meaning this age that you used here in this model, this age here, variable in the model, is not necessarily important. So we want to negate this null hypothesis that there's no importance of age. Age is not an important variable in the model. So we need to reject this null hypothesis, and the way to reject it is if this value is less than 0.05. As you can see here, the F value over here is 4.428, whatever it is the number, but e to the minus 11. This means that you multiply this by 0.10 zeros and 1. So it is really less than 0.05. So we say here all the independent variables in the model collectively important in predicting or in explaining the variance in the dependent variable. This is a general way of writing things. But over here, we can write it by saying age is an important variable in explaining the variance in height. So that would be also a very specific interpretation of this F metric. All right. Okay. The fourth checkpoint would be, in fact, checking out if we have these values over here, the p-value of these values. However, in fact, I like to come back here at the very end. There are certain assumptions. One of the assumptions here is the assumption of normality. So do you see here at the same alignment? I'm going to add 4. And 4 will be the normality assumption of residuals. So the normality assumption of residuals, let me put this here like that. The normality assumption of residuals is found through the skewness and the kurtosis. If you forgot what the skewness and the kurtosis is, then please review your notes from the statistics class. So that will be the skewness of the numbers here are the errors. So we're taking the residuals as is. And the kurtosis here is the kurtosis of these residuals. Now, depending on the sample size, we will find out if the kurtosis and the skewness are within acceptable range. And the way to do this, in fact, I have here, let me find you the slide. What happened? Okay. Seems like it is not here, but I think it is here. It seems not to be in this set of slides, but if you guys noticed, in this Mao Palace, I think I have it. I have a nice table. Here, the sample size and the lower and the upper bounds. So it is in regression analysis tool pack in the Mao Palace. So please copy that. And in fact, I'm gonna probably adjust the file again and put it there. So I'm gonna put it here in Q, around Q or P 24, something like that. So let's take a look. Our kurtosis 0.26, and our sample is between 10 and 12. So when we take a look at the kurtosis, we find out that our value lies in within the minus 1.37 and 1.376. So it is normally distributed. Usually I don't look at the kurtosis when the data is continuous. We focus on skewness when the data is continuous. But when your data is of an ordinal kind of form, like a Likert scale, or we call it an anchored scale from 1 to 5, then we use kurtosis rather than skewness. But let's take a look at the kurtosis. Also, the kurtosis here is 0.594, and it lies in within the range. So we are normally distributed based on our sample, very small sample size. So we are normally distributed. So that is really good that we are normally distributed. The another assumption that we are going to take a look into is the assumption of a heteroskedasticity or homoscedasticity assumption. Homoscedasticity. Let's hope that I wrote it correctly. I'm going to take a look at the spelling later. So the homoscedasticity is very difficult for you to probably pronounce. I like to take it, let me just move these guys a little. Let me take them Control X, Control V. And I would like to find the absolute residuals. So I'm going to find the absolute residuals here. And that is found by taking ABS for absolute, and here is the residual. And this is the absolute residual. Right? And then this is the values. With homoscedasticity, we are going to plot the, basically we are going to plot the two variables and look into their correlation, or look into their behavior and see if there is any kind of relationship between them or not. And these two variables will be the predicted and the absolute errors. So basically you are going to focus on the fifth here for homoscedasticity. We're going to focus on the absolute residuals with no sign, and then we are going to take a look at the predicted height, this value that we got it outputted for us already. We knew how to get the predicted height by hand from the formula here, but it is saving us a lot of time to just use the predicted height, and that is produced from the analysis toolpack. So basically we need to get a scatter plot. So I probably made a mistake. I probably should have added here a column for absolute residual so that it's easier for me to select the values. So let me just back, I'm sorry, I forgot how I did this very smoothly. So this is to be done very smoothly because we're gonna select the range, right? These are the absolute errors over here. All right, so now we can use the absolute errors and the predicted values in a scatter plot. And we want to make sure that over here is the predicted and over here is the absolute errors. So basically, I don't think this is the case. This is the no, this is the case actually. This is the predicted and this is the absolute errors. That's totally correct. If you're not getting the right order, but you will, you know how to do it. You go to insert and you go to charts and start from there. All right, we got the right order. So that's why I like to put it over there. So this is the predicted height, right? And this is the absolute residuals. If you want, you can just bold these. And now you can see that it is very difficult to have a linear line, but let's check if we have a linear line here. You add the trend line and make it linear and have the r squared if you want and have the equation if you want. And you can see here that there is no relationship, almost no. Oh, I'm sorry. I want to get rid of this and I'm going to put the line in format the line in, I put it in red color. How about that, guys? So that you can see it better. So let me put it in this very bright red. So this is the line. And as you can see here, when x increases, which is the predicted height, when the predicted height increases, actually the y, which is the absolute errors, increase by only 0.00000009, basically not much, or decrease. Actually, here's minus. This is the negative sign here. So there's really little amount that is affecting this by this, and it's a flat line. It's not going up, it's not going down. So basically with homoscedasticity, for the normality assumption, we're looking into if the relationship, let me put this aside, if there is a relationship between the predicted values and the absolute errors, or the magnitude of errors. So let me explain this homoscedasticity assumption very quickly right now, but I will dedicate more time on Tuesday to talk about homoscedasticity visually and through the Prussian and test. There's another test that we use to mathematically take a look and see if there is any if the relationship between the predicted height and the absolute residuals is any alarming. It is alarming. Over here, I won't run the test because it's very obvious the linear line is horizontal. It doesn't have increasing or decreasing. So obviously that the r squared is also very low. It is less than 1, less than 0.1 even. It is 0.0002. So this doesn't really affect the variation in absolute errors. So this means that all our errors, as we've seen earlier, do you remember when we took a look at the errors here? The errors are random, basically. And over here, we can take a look again. And I would like to explain what is homoscedasticity. Homoscedasticity is basically our linear plot. If you take a look at the linear plot, you will find out that all the points are very close or within the same distance away from the line. So they are all very close to the line, and the distance away, the maximum, the boundaries, the upper and lower boundaries of the distance between the actual and the predicted is basically, we can draw it as being, let me take this, as being, this is up to here, and basically, so basically this range over here, all this range from the, I am trying to be precise, this is roughly the range that these points are varying around and distributing around the line, meaning that this range, I can see it as being stable. Homoscedasticity means that the variance is almost stable, almost the same, almost consistent. However, if you take a look at other topologies, for example, some data that looks like that, these are actual values, for example, that looks like a hone, that looks like a speaker, or a hone. In this case, probably the line will look something like that. And in this case, as you can see, this range is different. Do you see that? So the errors, the magnitude of the error, it changes as the predicted value increases. Isn't this the predicted value increases? This is, I know that for you, this is the predicted value over here. So I understand that. So if you kind of flip the chart, it's the same situation. As the value here increases for the y, the predicted, you will find out that this error also, as you can see, also increases. So as you can see, as this predicted value increases, these errors over here increases. Or the values could take this topology, as the predicted value increases, here the errors also decreases. So basically there's a relationship. If there's a relationship between the predicted values and the error term, that means that there is something called heteroskedasticity. Something really we don't like. Hetero means not consistent. We look for something like this, homoscedasticity. Heteroskedasticity, when the a variation of these points around the line differs. So it's either increasing or decreasing, or either sometimes increasing, then decreasing, then increasing. For example, over here, it is, for example, here, increasing, decreasing, like that. So this is decreasing, then increasing, then decreasing, for example, the behavior. Then there's a certain behavior, there's a certain pattern here. We don't like that. We call this heteroskedasticity. And with heteroskedasticity, this violates the assumption of homoscedasticity. So homoscedasticity, homo is the same, consistency, right? So homo means that there's a consistency. The magnitude of error, or the value of the residual, regardless of being positive or negative, is almost consistent. This is good for us for linear regression, and we can proceed with the assumptions. So in our case here, as you can see, a different way. So there are two different ways looking into homoscedasticity. We can either take a look here at the plot. This is why we start our investigation with plotting the x and the y. But sometimes when you have multiple linear regression, it's very difficult to plot more than one x and y and put them all together. So this is why we're going to talk about another non-visual kind of test for homoscedasticity. So over here we can say, after we, for the normality assumption, for example, we can say the residuals seem to satisfy the normality assumption. Or you can find me saying the normality assumption, or you might find me saying the error terms, or the error term satisfy the normality assumption. So based on this visual, are no concerns of heteroskedasticity. So basically, the error terms also satisfy the homoscedasticity assumption. I think I'm writing skedasticity wrong, but let me for now just to proceed. All right. Maybe not. All right. So this is how you comment on that. The last thing that you need to look into, which is number 6 over here, is basically the multicollinearity, right? So there's another assumption called multicollinearity. With the multicollinearity assumption, we are basically saying that we would like to make sure that the independent variables are not correlated. Since we have only one independent variable, we don't have other independent variables, then we are not necessarily gonna test for multicollinearity. So multicollinearity only used for linear regression. When you have only one independent variable, you don't use the multicollinearity assumption. I think the video is getting really long, so I'm going to stop here. And I hope today you had a glimpse of the main assumptions. However, I don't want to stop here before I say, since we are satisfying the normality assumption and the heteroskedasticity assumption, so we are satisfying the normality assumption, that not we, but the error term, and the error term also satisfying the homoscedasticity assumption. We also checked for any autocorrelation and everything was already fine and random. Then we are going to say now that these coefficients, this coefficient in particular for the independent variable and its p-value are valid. So to validate, to say that this p-value is actually valid, we need to take a look at the assumptions. So with linear regression, we first run linear regression, then we take a look at the errors and the outliers and the assumptions. Then we go back again to these coefficients and say this coefficient is valid. So we say this is the last number here. I put here 6, multicollinearity, to program you in the future for multi-regression analysis, that we need multicollinearity first. So we're going to say 7 here. So 7. The p-values, which are the significance reflecting here reflecting the significance of the coefficient over here, are valid because the assumptions, which assumptions are we talking about? We're talking about the assumptions of linearity or error terms, normality, sorry, not linearity, normality, and homoscedasticity and multicollinearity, or this is for multilinear regression, are also validated. So because these are validated, this is validated. And now let's talk about the interpretation. The interpretation is as follows: as age increases by 1 month, height increases by the coefficient, which is 0.6349 centimeters, or increases by an average or an estimate of, or by an estimated 0.6 centimeters. And here I would like to stop. So let me summarize. We can use the data analysis tool pack under the data tab to produce the output of linear regression. The first step is to interpret the R squared, which is basically the squaring the multiple R, which is the Pearson correlation. And then we can say that the independent variables explains a total of 98.9% of the total variance in the dependent variable. In our case, we have only one independent and one dependent. We always have one dependent in regression. So we say age explains a total of 98.9% of total variance in the dependent height variable. Then the second checkpoint is here. The second checkpoint is finding out if we have any outliers. So first of all, we need to take the 2 times the standard error. So we look into values outside 2 standard errors, and then we find if any of these values are greater than this. We actually try to find how many values are lying within 2 standard errors. We find out that 95% or greater or above lie within 2 standard errors. So we don't have any problems with outliers, because if we have outliers can, why do we check this? Because the outliers can influence, can exaggerate or underestimate the coefficients. They manipulate the value of the coefficient. Not necessarily, sometimes they might actually yield to, cleaning outliers might yield to a better p-value, but the main concern is we have any outlier that the outlier will manipulate this coefficient. So it will yield to a higher increase or to a lower increase because it is an outlier. Yeah? All right. So this is our concern here is resolved. There's no outliers that will affect or exaggerate the value of the coefficient of the independent variables or variable in this case. So we say that 100% or whatever 95% or greater lie within 2 standard errors. So this means that there are no outliers that will affect the coefficient value, might exaggerate it or might underestimate it. All right. Normality assumption of residuals, we take the kurtosis and the skewness. Basically, mostly researchers will look into both kurtosis and skewness. However, if you are really desperate in some of the cases, you will find out that your data satisfies the skewness, but not the kurtosis. If your data is continuous, then it is all right. I'm telling you right now, it is all right. Just look at the skewness, basically, and forget about the kurtosis. But if your data is ordinal, for example, it is a Likert scale or Anker scale from 1 to 5 or 1 to 7 in your research, and for any reason you are investigating the normality of a certain data, you probably want to look at the kurtosis more than the skewness. So over here we found out that within our sample size of 12, between 10 and 20, we found out it lies within the range. Now, homoscedasticity is an assumption of whether the predicted value increases or decreases as the magnitude of error behavior increases or decreases. If the error is random, there will be no pattern. So this is basically finding out if there is any pattern in the error, increasing, decreasing, increasing, then decreasing, then increasing again, and so forth. I don't like only the visualization here in terms of a linear. Why? Because the pattern cannot always be linear, either increases over the predicted or either decreases over the predicted. Yeah, like that. Sometimes it could take the form of decreasing, increasing, decreasing. The data might look something like that, for example, and this is the line. So this is decrease, increase, decrease. This is not linear, because linear is as this increases, increases, decreases. This is as this increases, this actually increase then decrease. No, it should only one description. So for this purpose, I don't like to use necessarily only visualization, and I like to use another test that I will add. So the author in his book, he didn't give us a test, but I will give you the test. But for now, I know that there is no homoscedasticity, not only because I plotted this while I just told you that I don't always trust the plot, but because also I looked into this pattern. There's no autocorrelation, everything is all right, and there's no pattern, so it's all right. I'm just gonna proceed. All right? And this is it. Multicollinearity is basically an assumption that we will get introduced to it in the next session, in the next class together on Tuesday, when we have multilinear regression. I thought I will introduce you now to the 1, 2, 3. Did I forget to talk about 3 in the summary? 4 and 5, and mainly here 7, so that you will get used to this again and again and again. So next time I will see you hopefully on Tuesday, healthy and happy, and we can work on more data sets and understanding in depth the homoscedasticity through another test, and we also investigate multicollinearity. Thank you so much all. I'll see you on Tuesday.